these ideas that we've been using for our polynomials, and then also reminding ourselves of what some of these definitions are, like our degree and things like that we've probably seen previously but haven't really used yet, but will be super important to us in this chapter here. Right, so we're working with our polynomial rings, which are going to be polynomials where the coefficients come from a specific ring. So we'll use a notation R and then our brackets X. Almost always we're going to use X as our indeterminate, but you can use Y or Z. You just want to make sure you don't use a letter that's already used inside of your ring itself. We really are thinking of these as infinite sums instead of finite sums, just so that our multiplication, we can come up with a nice definition for it. We can still come up with a definition if it's finite sums. It's just a little bit more clunky about understanding where it's going to end when we're doing that multiplication. Okay. Right. Some things to point out are we're treating these elements as polynomials and just polynomials. We can find more information about them if we think about them as functions, but then we have to state what the domain and codomain are going to be there. And then distinct polynomials might not be distinct functions. As an example, we found here in Z2, I came up with polynomials with different coefficients, but as functions where the domain was Z2 and codomain was Z2, I got the same exact outputs for all of my inputs. So they really were the same functions, even though the polynomials were different inside of our ring. So a lot of the times I'll just write f and g instead of f of x and g of x to kind of remind us we're just thinking about them as polynomials. But we can actually get more information out of them if we think about them as functions as well. So sometimes we'll go back and forth between these ideas here. Right, we looked at our definition for addition and multiplication, which was just supposed to be like a generic way to write this out that looks the same way as we're used to when we add up our polynomials or when we multiply our polynomials. Addition is the simplest one because we just combine our like terms. So any of the ones where the index is the same, we just add up the coefficients there, and that'll give us the new coefficient for that specific index. But really the goal when we write these definitions is to say, when I add these or when I multiply these, this is the exact polynomial it's going to look like. This is the most simplified form because it always needs to look like the coefficient times x to the power. Okay. For our multiplication, we really want to do the foiling and then collect our like terms. So here, when I multiply these coefficients, if I look at the power for x to the j, or if we look at the coefficient for x to the j, I think about which indices are going to add up to j. Because when I do my foiling, it'll give me that specific power. I multiply those coefficients. And then all the ways that I can do this, I'm going to add them together. So the adding together is really collecting the like terms. The multiplication is really doing the foiling part here. Again, this is just formalism. The way that we actually multiply them, you can just do it as normal. It's only really important to us when we want to do proofs for general polynomials. We can't do the foiling because we don't have a specific a polynomial to work with there. Okay, some things also, right, we're not going to check all of the axioms that we need for our ring here, just because they're not going to be illuminating here, and they just work in this nice way. So we know the addition that we defined is going to be a binary operation, so it's going to be well defined, and when I add two together, it'll give me back a polynomial. We know it's going to be commutative here. We'll have our zero polynomial, which we can either write as 0 sub r or 0 sub rx. They really are the same thing here. It's going to be our constant polynomial, where I can just think my constant term is 0 here. If I think infinite sum, really all my coefficients are equal to 0. If I want to find an additive inverse, I just find the additive inverse of all my coefficients, and that gives me my new additive inverse. That way, when I add them together, when I add them index by index, I'll get 0 for all my coefficients. My multiplication is going to be associative, and then it's going to be left and right distributive over the addition. So it does actually give us back a ring, even though we didn't check all of these pieces here, we do get them. Okay, we also know if the ring where our coefficients come from has unity, Then the constant polynomial, that's just the unity, so it's 0 for everything else, is going to be the unity of our polynomial ring. If the ring is commutative, then the multiplication is going to be commutative, and so the full ring, Rx, is also commutative here. Right, and then these are just some terms that we want to be a little bit more comfortable with, that we should have seen before, and then also formalizing them a little bit more. So the a sub i's are coefficients. Again, a zero polynomial is going to be the one where all the coefficients are equal to 0. When we have a non-zero polynomial, you can actually talk about its degree. If it's the zero polynomial, we'll either say it has no degree, or we'll say it has negative infinity as the degree. Really, it just depends on the textbook, on what you might see show up for this year. And I don't think that our textbook actually states us out directly here. So most of the time we'll just do the cases where it's the zero polynomial separate from what we're working with here. But our degree is going to be the one, the number, so that so the number n, so that a to the n is the biggest coefficient that's not equal to 0. So if I write it in decreasing order for my powers, it'll be the first one that's showing up. That power that's showing up is my degree of that polynomial. Really how we are used to thinking about them with our polynomials. Okay. Right, our leading term is going to be our an x to the n, where n is going to be the degree of our polynomial. We're going to call it polynomial monic if the leading coefficient is 1, and that's provided that the ring has unity. If it doesn't have unity, then we can't have monic polynomials. And then a monomial is going to be one that just has one term. So only one of the coefficients is non-zero and the rest are 0. And then we also add in the 0 polynomial into that list as well. Okay, so the theorem that we were working with the last time, we started to prove, but we didn't finish, was thinking about what properties of the ring R does Rx get inherited, the polynomial ring where the coefficients come from R. And so the thing that we'll see here is if the ring I'm working with is in an integral domain, so here I called it D, and then the polynomial ring with D as coefficients is also going to give me an integral domain. So the goal of this proof is to show if you have two non-zero elements, so here 2 non-zero polynomials, and we multiply them together, we shouldn't get back the 0 polynomial, right? There are actual cases where I'm not working with an integral domain and my degree goes down when I multiply, or it can go down when I multiply. But with integral domains, it turns out when I multiply two non-zero polynomials, the degree of the product is just the sum of the degrees there. So if one is degree 1 and the other is degree 2, when I multiply it, I do get degree 3. But it's important that I'm working with an integral domain. If it's not an integral domain D for my coefficients, the power can actually go down all the way down to actually give me 0 as my polynomial. So I don't necessarily get an integral domain if my ring is not an integral domain itself. Okay, so let's look at the proof that we were doing here. Technically, we would need to show that it is a commutative ring with unity and no 0 divisors. But we already know that the commutative part and the unity part, it inherits from the ring itself. Those are a little bit more obvious, but the no 0 divisors takes a little bit more work. So that's what we're going to do here. So we're going to take two polynomials, f and g, and really we want them to be non-zero polynomials. So that's what our star is here. So that's saying that not all of the coefficients are equal to 0. I can find at least one coefficient that doesn't equal 0 for both of my cases here. And so really what that's telling me is that I can actually think about the degree of each one of the polynomials. I'll call one n, I'll call one m. And then the goal is to study what happens when we multiply them together. The goal is to show it doesn't equal the 0 polynomial. And really we'll do this by showing that the degree of the product is going to be adding up the degrees of the pieces there. And so it can't equal 0, or it can't equal the 0 polynomial, because it's going to get a degree back out here. And it's actually going to be bigger than the ones that we started with. Okay, so here we're going to multiply our two polynomials. So here we'll get f times g. Okay, and when I multiply these together, right, my definition says I'm going to get a new polynomial where my coefficients, and I should use a different index. I'll use j here. Where we stated earlier how to multiply our polynomials, so this is where this is going to show up. So here my CJs, or the coefficients that I'll have, are going to be a sum also. So I'll replace my CJ with a sum, where I'll say I want I plus k to give me back j. And then I'm going to multiply my a sub I and my b sub k. That's how we defined our multiplication for our polynomials here. That's what that specific coefficient was going to be, right? Again, in practice, we don't actually use this, but with our proofs, we have to use this exact definition to tell us what's going on here. And that will be my coefficient attached to my x to the j here. Okay, so my goal is going to be to study what this is here. And really the way that we're going to show it's not the zero polynomial is by showing that it has some degree. So I'm going to have some largest coefficient, some largest power showing up here. And that's really the part that I want to study. Okay, so here we want to decide what is going to be the largest one, right? If I just think about writing them in this form, where I said f has degree n, so I know my largest or my leading term is a sub n x to the n. My degree of g is m, so I know I'll have b sub m x to the m. Then the largest power that I could possibly get is going to be n plus m. And there's going to be exactly one way that I'll get that power. It's only going to be when I multiply my leading coefficients here. Okay, so when we do this, we'll get back a sub n, b sub m, x to the n plus m. Okay, that's the very first term that I get. That's the highest power that could show up. Okay, possibly the coefficients could give me back 0, but I know that's the biggest that could come up here, and I'll have some smaller terms. But for us, all we'll care about right now is what is this biggest one, and what's the possibility for the coefficient showing up here. Right? Because if I can show this coefficient is not equal to 0, and this is the biggest one, then my degree has to be n plus m. Okay, so here, what can we say about these two coefficients here, my a sub n and b sub n? Where are they coming from, and what do I know about them? Yep, so this one's coming from my f, and this one's coming from my g, where f has degree n, and g has degree m. So what does that tell me about the leading coefficient if it's degree n or m here? What is a leading coefficient not allowed to be? It can't equal 0, my coefficient. So if my leading coefficient is 0, it's not actually the leading coefficient there, right? It has to be the largest one that's not equal to 0. So because these are the leading coefficients of these two non-zero polynomials, then a sub n and b sub m cannot equal 0. Since they're coming from the leading coefficients of non-zero polynomials. Okay, but these are just coefficients. So they're coming from my integral domain D. So what does that tell me about their product? If I have two non-zero elements, the product can't be 0, or else it gives me back a 0 divisor, but my integral domain has no 0 divisors. Okay, so what this is telling me is that f times g doesn't equal 0, which is really all I wanted to show. Is I could find one coefficient that doesn't equal 0 here, so I don't have the 0 polynomial. So we can say our polynomial ring has no zero divisors, because whenever I multiply non-zero polynomials, I get a non-zero polynomial back out. No zero divisors. So it is an integral domain. And we can actually say a little bit more outside of our proof here. When our ring is an integral domain, then when f and g are polynomials with coefficients from D, but if they're not the zero polynomials, so they're not the zero elements, then we can precisely decide what the degree of their product is going to be. Right, through our work, we're seeing this is the biggest power we'll see show up. This is non-zero. And so this has to be our degree of the product here. It has to be n plus m. So here, when I have an integral domain and I have two non-zero polynomials, I multiply them together. The degree is now going to be the sum of the separate degrees. Again, this is not always true. If I work with, let's say, z sub 6, z sub really any composite number as my coefficients, my degree can actually go down when I multiply two things together. Like if one of my polynomials had leading coefficient 2 and the other had leading coefficient 3, when I multiply those together, it would give me back 0 mod 6, and it would make my degree go down, right? So when I have an integral domain, things are going to work really nicely when I multiply together. I can't go down, and so I won't get zero divisors here. But when I have zero divisors in my integral domain D, I could possibly get them in my polynomial ring as well. Okay, so we did a little bit more than what we needed to, but this is going to be helpful for some other theorems that we'll look at. Okay, so lots of times the properties of the ring are going to be inherited to the polynomial ring, but this is not always the case. So one thing that you might think is if you have a field for your ring, then the polynomial ring with that as its coefficient should give you back a field, but that's not the case. We're not going to get all the multiplicative inverses when we have coefficients have multiplicative inverses. Bless you. And it turns out if R is a commutative ring with unity, then the units of the polynomial ring are just going to be the constant polynomials that were units from the ring to begin with, right? So if f was a field, that would be all my coefficients except for 0. All my constant polynomials except for 0 would be units, but nothing else would be. All the other polynomials that I have, if I have an x, so not a constant, are not going to give me back units inside of my ring here, right? So this is kind of the most general form that we can say this. We can decide exactly what the units are going to be. They have to be constant polynomials, and they have to come from units from the ring to begin with. Okay, so here, again, this is really saying that the units of my polynomial ring are exactly the units of the original ring are. Okay, so I really think these constant polynomials are going to give me back all of the possible units here, but this is not the same as just the leading 0. Right, I have a bunch of other elements in here that are not going to give me back units. I don't have their inverses showing up in my set here. Okay, so what we're going to do is we're going to show if we have a commutative ring with unity, then what we're going to be able to show is if you have a unit, it has to give you back a constant polynomial. And the only constant polynomials that are going to be units are going to be the ones that were units from the ring itself already. Okay, so we're going to take two non-zero polynomials. So we'll put our star here to tell us it's not the 0 element. So it's not the constant polynomial with just zeros showing up for your coefficients. Where we want these to be inverses or units. So I can write f times g to give me back the unity inside of our polynomial ring. Inside our polynomial ring, what is our unity? Which polynomial is going to work as our unity? So when I multiply by anything, I'll get that anything back, just our one. And this is dependent on our ring having unity, or R having unity. If R has unity, then the polynomial ring with R's its coefficients also has unity. And the constant polynomial with just one is exactly going to be the unity here. But here we're assuming that our ring has unity, so I know our X also has unity here. So I know that this has to be equal to, right, the unity in Rx, or I can think this is the same as the unity in R. It's just my constant polynomial where the constant is equal to 1. Okay, so here we'll have, we want to look at, or what we can study is the degree of their product to give us some more information, to tell us what f and g have to be here. Okay, so here, these are units of our ring. So these are non-zero divisors, right? So when I multiply non-zero divisors, right, I shouldn't get 0 back out here. But I can actually say a little bit more. We can use the proof that we did earlier to show us that we can really add the powers for what the product is equal to here. Okay, and so here, and actually I should put something right before this. All right, let me actually change the order, 1 second. So we have degree of f plus degree of g gives us back the degree of f times g. But we said that f times g is exactly 1, the constant polynomial. And what's the degree of a non-zero constant polynomial? Right, so when I write something like this, and the rest are smaller terms, the n is telling me what my degree is. So for my constant terms, it's going to be 0, because I can really think of my constant term as a sub 0 x to the 0. Right, so anytime I have a constant polynomial that's not the 0 polynomial, the degree is going to give me back 0. Okay, and so something else to know is that our degrees, the smallest it can be is 0. I can't have a negative degree here unless I think about my 0 polynomial, but we really treat that one separately. Okay, so here I want to think, what are the two possibilities, or what are the possibilities for my degree of f and g so that they add up to give me back 0? So what are the possibilities for these degrees here to add up and give me back 0? So they have to have opposite signs, but they can't be negative. So it's just 0. The only way I can add up non-negative numbers to get 0 back out is if they were both 0 to begin with, right? I could rearrange it, right, to see degree of f is equal to negative degree g, but because both of these are non-zero polynomials, they have to have degree at least 0. And so the only way that'll work if it's both of them are degree 0 here. Okay, so here, the only possibility is that the degrees are equal to each other and that they're equal to 0. Only polynomials of degree 0 are our constant polynomials. So f and g are, again, non-zero constant polynomials. So I can say f is equal to some element in my ring, and G is equal to some element in my ring. So these are our constant polynomials. I don't see any x's showing up here. I just see the constant coefficient that comes from my ring R. Okay. But when I did my multiplication, this was saying when I multiply R times S, I should get 1 back out. So the only ones that will do this are going to be the ones that are already units in my ring R. Okay, so if I have a polynomial that has an inverse, so that is a unit, it has to be a constant polynomial, and in particular, the constant has to come from the units of R. Okay, the only other thing to show is that the units of R actually do give us back units in Rx, right? That it does go in both directions, that we do get double containment when we're thinking about these sets here. Right, so this is telling me that the units of Rx sit inside the units of R. And then the opposite direction is a little bit more clear. If I take units in R, multiply them together, I think of them as constant polynomials instead, right? I can multiply them together and get back a 1. And so I really do get the opposite containment as well. So these really are the same. But in one case, I think of it as a polynomial, a constant polynomial. And in the other case, I just think of it as an element inside my ring R. Right, so this is really saying the units of Rx are the constant polynomials that are units inside of R already. Right, that's really what that notation is trying to tell you. Okay, great. So really that's telling me if I start with a field for my ring, the only units that I'm going to have, let's say called the F, for the polynomial ring where my coefficients come from F, so Fx, are going to be the units that came from F itself. So it's just going to be the non-zero constant polynomials, but things like x squared, x cubed, x to the fourth are other polynomials that don't have inverses. So they're not units. And so I don't get a field back out for my polynomial ring here. Okay, but one thing that we do get is our division algorithm, and we're going to remind ourselves of what that means. Just like we've done previously, really we only did this for integers. We thought about how do we divide our integers, what's the process to figure out what they are, and how can I write this out formally. We can do this with our polynomial rings as well. As long as the coefficients are coming from a field, then you're allowed to use this this algorithm here, this division algorithm. And it's really the same way that we do it usually, right? Where we do our long division for polynomials. This really is giving us that in the same information, just like we do long division with our numbers as well. So let's remind ourselves what the division algorithm tells us. Okay, so here, if I take two integers, but I'm going to take one to be positive, then I can find a unique two unique integers, Q and R. So then I can write A as a product of B plus really some remainder, where the remainder has to sit between 0 and B. Really the thing that we think about here is how do we divide A by B, and then we'll get some remainder. And after undoing that division, we can write it as a product instead. So we'll look at an example to kind of remind us where is this coming from, what would the A, B, Q, and R be here, and then how do we translate this information to have polynomials instead, and what would this piece be here when we have our polynomials? We'll see it has to do with our degrees instead. Okay, so let's say we want to do 82 divided by 7. Here, do our long division. Okay, and we'll start from the left. We'll see 7 goes into 8 once. And then we'll do 1 times 7 and subtract this. Okay, and I'll get 1 back out. If my difference that I took here was 7 or bigger, that means I didn't pull out enough, right? Then I could have had something bigger that I could have multiplied by 7 to subtract here. So here, whenever I'm subtracting, I should always get something smaller than my 7 here. Okay, and then I'll pull down my 2. And I'll think, how many times does 7 go into 12? It goes in 1 nicely. Twice would be 14. That would be too far. So I subtract 7, and I'll get back 5. Okay, I ran out of digits, so I stop here. So what this is saying is that 82 is equal to 7 times 11, but I have this remainder of 5. Okay, so I could always think about how many multiples of 7 do I have in 82? It might not divide it nicely, so I will have this remainder showing up where the remainder could be somewhere between 0 and 7 here. So here from our division algorithm, 82 is my A, 7 is my B. That's the thing that I try to divide by. Q I can think as my quotient, and R is going to be my remainder, which in this case is R5. And what we're seeing is that we do get the statement here that the remainder that we have is going to sit between 0 and what we were dividing by. That's 7. Okay, if it was something bigger, then we didn't pull enough out when we were doing our division here. Okay, and so anytime I write it in this form, where my remainder has to be between 0 and what I divided by, these two numbers are going to be unique. I'm not going to have options on what they could be. I can only write it in this one specific way here. Okay, so again, what we want to do is think about what the division algorithm is going to look like when we're working with polynomials instead. And here we're going to allow the coefficients only to come from fields. When I have fields as my coefficients, then this algorithm is going to work out nicely. Okay. Right, and again, the things that we need to decide is what can I say about my functions? Do I have some form of inequalities between them? Right, because they're not numbers, I can't think about f is bigger than g here, but I can think about what their degrees are going to be and then compare what the degrees are here instead. Okay, so if we have a field f and we take 2 polynomials from the polynomial ring where f is my coefficients, so I'll take little f and little g, and I want to take g to be a non-zero number or non-zero polynomial, and really we can think up here. I could have technically done negative numbers here, but it just makes it a little bit nicer to just work with positives. But the thing that we did restrict ourselves always is that we can't do 0, because we want to think I can't divide by 0, so I'm not going to have a way to answer this question. So similar here, whatever I think is what I'm dividing by can't be the 0 element there. So it can't be the 0 polynomial in our case here. So this is the polynomial 0. Okay, so when I have 2 polynomials inside of fx, one is non-zero, then I can find unique polynomials, q and r. I'll use the same letters here, so that we can say a similar thing. I can write f as a product of g plus some remainder, right? And I can write these without the x's or with the x's, but this is really what I'm doing here. And the extra restriction that I want to put on this is that the degree of r is going to be less than the degree of g. Okay, and we know the degrees of all of our polynomials are at least 0. So we always have that 0. We can really think I have a 0 less than or equal to the degree here, less than the degree g, to give us like the same statement. Something else that we want to be careful about is, what if it divides it nicely? Then I have no remainder. My remainder could be the 0 polynomial, but my zero polynomial doesn't have a degree. And so I want to treat that differently. So I'm going to say with this inequality, or where the polynomial is zero itself, the polynomial, the zero polynomial. But again, the zero polynomial, we always have to kind of treat differently because it doesn't have a degree. Or I can think it has negative infinity as its degree, and then the statement would still be true. Okay. So let's look at an example here of how we would find the Q and the R with these specific ones. But again, this is just going to end up being long division with your polynomials. So here we're working with two polynomials f and g inside of Z5. Notice that this here is a field, the ring Z5. Because the 5 is prime, then I immediately know that it's a field. I'm not saying that the polynomial ring is a field. This is not a field. I'm just pointing out that where my coefficients are coming from is a field, and so I'm allowed to use my division algorithm there. If it wasn't a field for my coefficients, I'm not guaranteed that I'll have this nice way to rewrite my polynomials in this unique way as well. Okay, so we'll do our setup similar. We'll put exactly. So the coefficients give me back a field, but the whole ring here is not a field because the only units in here are going to be the constant polynomials 1, 2, 3, 4, which is not all of the elements inside of that ring. Yep. Okay, so let's do our division here. Let's do it in this way. So I'm going to do my division where the one with the bigger degree is showing up underneath here. I can do it in the opposite order as well, but I don't get like as nice information as I usually do. Just like if I did something like 2 divided by 5, I get something smaller than 1. I still can do that and I can still get an answer. But really the things that we want to do are going to be in this order instead. Okay, but the division that we'll do will look really similar to what we did with our numbers. We look at our leading coefficients. So I have x squared and 3x to the 4th. And I want to decide, what do I multiply to x squared to give me back 3x to the 4th? And here I'm working in Z5. I'm going to multiply by 3x squared. I'm going to place that over my 2x squared just to keep it organized. And then just like we did before, I'm going to multiply these together, so I'll have the FOIL. And then I'm going to subtract it off. So I'm going to multiply this whole thing by my 3x squared. So I'll get 12x to the 3rd power, but what would my 12 be in Z5? Okay, so I get a plus 2x to the 3rd power, and then a plus 2 times 3 to the times x to the 2nd power. So it'll give me back 6, which is 1 mod 5. Okay, so these are the things that I'm subtracting off. And we purposely did this so that the leading terms would disappear. So really bumping it down a degree, or at least 1 degree. So I'm going to have x cubed minus 2x cubed, which I can leave as just negative for now. Or I can translate it to think, what is that coefficient in Z5? I could have replaced it with 4 instead. But maybe we'll do a little bit more calculations and then just simplify it at the very end. Okay, and then I'll do my 2x squared minus x squared. So I just have 1x squared left over. And then I pull down the last term that I have that I didn't use. Okay, and then I continue my process again. This is going to be the last step that we'll have. I want to look at my leading coefficients, and I think, what do I multiply to x squared to give me back negative x squared? I need a minus x. But here I do want to think about it in Z5. What would my minus x equal here? Plus 4x. Right? My -1 is the same as +4. So that's where this is coming from here. And then I'll do the same process. I'll multiply 4x to this entire polynomial and then subtract it down here. Okay, so here when I do this, I'll get back 4x cubed plus 16x squared. But I am going to reduce that one just because it's so big. 16 mod 5 will give me back 1. So I'll get plus x squared. Okay, and then I'm going to do 4x times 2, which gives me back 8x. And then mod, did I do that right? Yep, and that should give me back 3x. Right, then my 2 times 4x to give me back 8x, which is 3x mod 5. Okay, now I do my subtraction. And this is going to be my last step, so I can do my full reduction here. So I'm going to have minus x cubed minus 4x cubed. And what should I get there? Yep. -5 or 0, so this one will just disappear. Which was the goal. Okay, and then I subtract my x squared with my x squared. So I'll get a 0x squared there as well. You notice this one does not have an x term, so I can think of it as 0x plus minus 3x. So I should get a minus 3x here. But minus 3 is +2 mod 5. And then I have my constant here minus a 0 constant, so I just have a +1 at the end. Okay, so here what I can do is I'm doing my f of x divided by my g of x. So this is telling me a way that I can write f as a product of g with some remainder. So here I'll have 3x to the 4th plus x cubed plus 2x squared plus 1. This is my full f of x. This is going to be some product of g of x. So I have x squared plus 4x plus 2. Here we're going to have this, which is going to show up in the product of 3x squared plus 4x. So this is working like our q. And then the remainder that I have is this 2x plus 1. And you don't have to put that last one in parentheses, but just to make it obvious what the whole polynomial is going to be here. Okay, so I found a way to write this as a product of my g with some remainder. And I want to see, is my remainder 0 or does it have degree less than g? My degree of g here is 2. And this is degree 1, so it did go down in degree, or it gave me back the 0 polynomial here. Right. If this ended up giving me, right, this is my remainder, something bigger than or squared or bigger, I would have to continue the process. I need to decide what else can I pull out. But I can always continue this process until the remainder gives me something back that has degree less than g, the thing that I'm dividing by. Right, so this is just regular polynomial division that you've seen before. But now we're saying when I have a field for my coefficients, I have a unique way to do this. And I can give you more information about the remainder. The degree of the remainder has to be smaller than the degree of what you're dividing by. Or it's the 0 polynomial if it divides it nicely, right? There's no remainder showing up. Okay, let's see our time. Okay, so I was going to do our proof here for our division algorithm, but I want us to have some more consequences from the division algorithm so we can do some more problems on the homework. So we're going to come back to our proof here, but just so that we can see how can we actually apply this, we're going to go through some corollaries that we have for it. So probably sometime next week, maybe on Monday, we'll actually go through the proof here. Okay, but it was pretty lengthy, so it's taken at least a full page. Just one reason why I want to skip over it, just so that we have enough time to to think about what some of these corollaries will look like. Okay, so again, we want to remember in our division algorithm, the ring that we're working with for the coefficients has to be a field. So anytime we have a corollary, again, the coefficients have to come from a field here. Okay, so if f is a field and I take a polynomial in my polynomial ring where the coefficients come from f, then I can actually say something about the remainder. Right, and really this is going to be some nice connection that we want to make about zeros of a polynomial and being able to divide by x minus that zero. So if a was a zero, if I plugged in a and I got 0 for my polynomial, I want to have some relationship about what does that mean? Can I factor out x minus a there? Right, that's really what we've learned, and we're going to make that connection here, but this is kind of the first step towards it. Okay, so if I find the remainder of f of x after I divided by x minus a, I'm going to get back f of a, right? So if if a is a 0, the remainder is going to give me 0 back out. And I can nicely divide my f of x and my x minus a here is really what my remainder theorem is saying. Right, and technically these are polynomials, but we can think of the functions induced by these polynomials where we'll tell you exactly what the domain and codomain are going to be. The easiest one to think about is the domain is going to be where the coefficients are coming from, and the codomain is going to be the same exact thing. So I can think of my polynomials here. F inside of my polynomial ring as a function from my ring to my ring. So from capital F to capital F. So it's going to induce some function here. But again, I can decide what the domain and codomain are, and it might change what my answers are or what the function actually is. But anytime we think about the function induced by the polynomial, we'll take the codomain and domain to be where we're taking our coefficients from, because we know that that's always going to work. If I plug in something from my field, I should get back something from my field if I plug it into my polynomial here. Okay, so here what we're going to do is we're going to use our division algorithm to divide these together. So our division algorithm tells us if I want to think about dividing f of x by x minus a, I can really think, write f of x as x minus a times some other polynomial, and you're going to have some remainder. So there's a unique way that I can do this, and I know I can always do this, where the degree of r has to be less than the degree of my x minus a, which is equal to 1. Or my remainder is going to give me back the 0 polynomial. Okay. So here, if I know my degree of my remainder is smaller than 1, what are my options? So we want to study our remainder here. And right now we know that the remainder, the degree of the remainder has to be smaller than the degree of what we divided by, my x minus a, which is exactly 1. And I want to decide what are the options for the degree then? Just 0. So either it has degree 0 or it is the 0 polynomial. Those are the two options of what I can have for my remainder. So we know this remainder we can think of as a constant polynomial where the constant is coming from our field. Okay, regardless of which one it is, they're both going to give us back constant polynomials, except one is either the 0 polynomial or you have a different constant. Okay, so this is telling me I can say something about when I plug in a into my function on the left, It should give me the same thing as if I plugged an A on the right-hand side anytime it's on X. But in particular, for my R of X, no matter what I plug in, I always get that same constant because it's my constant polynomial. It's really the same number showing up for all of my outputs here, right? Let's say if I said the constant polynomial was 1, then the function induced by it, if I plug in 2, I get back 1. If I plug in 3, I get back 1. It's always giving me that constant back out. If I think like real numbers, it'll give me a horizontal line, the same constant showing up here. Okay, so we're going to plug in A and we're going to see what happens here. If I plug in A on the left, I need to plug in A anytime I saw an X. Okay, but I have an A minus A, B multiplied to something will give me back 0. And then my R of A, I said, is always going to give me back C, because it's the constant polynomial, has no X's in it. Okay, and this is exactly my my constant polynomial here. Okay. Right, so what this is telling us is that f of a, what I get when I plug an a into my function, is exactly what I'm going to get as my remainder if I had divided. These are really the same exact thing. So if I did this long division and I got 5 back out, that's telling me if I plug in a to my function f, I should get 5 back out. And if I do all this work and my remainder is 0, this is really the important part. That's saying when I plug in a, I'm going to get back 0. So again, there's going to be some connection here about the zeros or the roots of our polynomials and how we can write them as factors with some remainder. Really, if it's a 0 remainder, it really factors out here, right? I can write f as a product of x minus a times something else in my polynomial ring.
Can you fix, since 4 r of x is 0, it should be 4 to the degree, or?
So either the degree, it depends on the convention on if your degree of the 0 polynomial exists or if you think of it as negative infinity. If you think of it as negative infinity, you can just leave it like this. If you think the degree doesn't exist for the 0 polynomial, I have to break it up into these 2 cases. So if I look back in my theorem, right, I said that either r of x has a smaller degree than g, or it's the 0 polynomial. So, yes, the r here. Yep. Right. In either situation, though, I get a constant polynomial, which was the goal, was to show that I got my constant there, that I got that same number no matter what. When I plugged in a for my function, I got the same exact number for my remainder. Yep. Okay. Right. So whenever we have these linear polynomials that we're dividing, where it's of the form x minus a number, right, again, this is going to give us some information about the zeros and how to factor our polynomials. But now we have a nice way, instead of dividing it all the way through, I can immediately tell you what the remainder has to be when I do this division instead. Okay, so if I want to find the remainder of f of x divided by x minus 1, we can apply the remainder theorem. Where we have a equal to 1. And I guess technically we need to think about where are these polynomials coming from? And I really need to think my coefficients should be coming from a field. So technically I should be saying, where does this polynomial live? Because it has multiple places that it can live. It can live in zx, it can live in qx, it can live in rx. We don't want to think about it in zx because z is not, the integers is not a field. So I can think of this as a polynomial with rational coefficients, or I can think of it as a polynomial with real coefficients. Really, this distinction doesn't really matter at this point. I can't really think the smaller one here. All that's really saying is that the q and the r that are unique are going to live in those specific places. But if I was working with my integers, I don't know that I can actually do this because maybe a fraction would show up for one of my coefficients. So I do have to be a little bit more careful about where we're actually living so that we have a field as our coefficients so that we can actually use our division algorithm here. Okay, so here all we need to know is what is f of 1? So here we'll get 1 plus 3 plus 5, or we'll get back 9. So this immediately tells me that the remainder or the remainder polynomial is the constant polynomial 9, which I can see as a polynomial with coefficients from the rational numbers. Again, I could have put real numbers here and it would still work out because both of these give me back a field. Okay, and we'll have a chance just to talk about this theorem, but we won't do it all the way through. And this is really the theorem that we want to be able to use. So if we have a field F and we have a polynomial from our polynomial ring where the coefficients come from the field, okay, and you take an element from your field, so little a here, then we're going to find out that little a is a root of the polynomial if and only if x minus a is a factor of the polynomial. And we're just going to remind ourselves, what does it mean to be a root? What does it mean to be a factor? But these are really the same ideas that we've had when you learned about polynomials back in pre-calculus. Okay, so here we'll say a root of f. So maybe we'll say b is a root of f. When I plug it into my induced function of my polynomial and I get back 0. So whenever I replace my x's with b and I get 0 back out, then I'm saying b is a root of that polynomial. Okay. We also want to think, what does it mean to be a factor? So we'll say g of x is a factor of f of x, and I need to say where. So I'm going to say inside of this polynomial ring. When the following is true, when I can find a different polynomial in the same ring, where I can write f as a product of g and f here. So here, f of x equals g of x times h of x. So I really can think here, if I did the division algorithm, I'd have 0 as my remainder here. Right, but the same way that I think of factoring with integers, I'll say, right, 2 is a factor of 6, because I can find 3 in my integers, so that 2 times 3 gives me back 6. So here I'll say g is a factor of f in this specific ring. If I can find something in there, so when I multiply by g, I get back f. Right, so I just want nice ways to be able to multiply my polynomials here. Right, so it turns out for this corollary that when you have a 0, really this is if and only if, so when you have a 0 or a root, then you know x minus that number is going to be a factor of the polynomial. And it goes in both directions. These are really equivalent to each other. If I have a factor that looks like x minus a, then a had to have been a 0 of the original polynomial here. Right, so ideas that we've seen before, but we're actually seeing why are these true? Why do we actually have this work out nicely for our polynomials here? Okay, so on Monday's class, we'll go back and look at the proof for our division algorithm. We'll again remind ourselves of some of these consequences, and we'll look at the theorem or the proof of our factor theorem as well. But for tomorrow, we're going to have our regular quiz at the top of class, and then we'll do practice problems, going over some of this polynomial section here. We don't have too much theorems that we could use, but really just to get us comfortable with our terminology and things like that. But if we don't have any questions, and I'll see you guys tomorrow. Have a good one.